Hey you guys, it's Thursday lunchtime and gonna give you guys a little bit of instruction today on equilibrium. We've been working through the packet 7 and the next topic is Q versus K and LeChatelier's principle. So let's jump right in. So let's review what we've learned so far. You can calculate K as the ratio of the products to the reactants raised to their powers that come from the coefficients from the balanced reaction. As long as you know the stoichiometry of the equation, then you can write an expression for the equilibrium constant. But what if it's not at equilibrium? If it is at any other set of conditions besides equilibrium, then we call that not the equilibrium constant, but Q, the reaction quotient. This is a capital Q. It's not to be confused with our lowercase q, which is heat in joules, and from our calorimetry. You remember that? So otherwise, these are pretty much the same. It's an expression of the ratio of the products to the reactants. We raise them to the powers of their coefficients from the balanced equation. We do not include solids or liquids, only gases and only aqueous solutions. Pure solids, pure liquids do not affect the equilibrium position. They are not part of the equilibrium process. They're essentially removed from the equilibrium process, and we solve them the same way. Let's see if I can move this out of the way a little bit. So we solve them the same way. The only difference is that for K, for the equilibrium constant, it has to be at equilibrium. And for Q, we plug in the concentrations that we have, whether we know or not if it's at equilibrium. Why would we do this? Well, a lot of times the question will say, is this reaction at equilibrium? And so we'll find Q, compare it to K, and then we will know. And so on our graph, we've worked a good bit with this particular reaction, the equilibrium that exists between the dark reddish-brown NO2 gas and the colorless N2O4 gas. Up until, so we start with all N2O4 and no NO2, and we reach equilibrium at this dotted line here at some point after the reaction has been initiated. Every set of conditions up to that time, we could solve for a Q, but we don't know, unless we know that it's at equilibrium, we can't get the equilibrium constant. So we need the equilibrium, where those concentrations level off is where the reaction has balanced out, has achieved equilibrium, and that's where we can find K. So before that point, we would find Q. Let's take a look. So mathematically, here's an example, hydrogen plus oxygen to form water. Mathematically, they're the same. Concentration of water squared over concentration of hydrogen squared times the concentration of oxygen. They're exactly the same. We just plug them in and solve for K only at equilibrium, for Q any conditions that you have. So how do we compare them? So when Q is equal to K, we would say that that system is at equilibrium. If Q is greater than K, then what that really shows you is that your products are greater than they would be at equilibrium. So it's like the reaction has gone too far to the right, and we have too many products and not enough reactants. Just thinking about that ratio mathematically makes sense. Q is greater. That means your numerator is too high. That means you have too many products formed. And what that tells you is that the reaction is going to shift to the left. The system is going to make more reactants to reach equilibrium. That means the reaction is going to run in reverse. If the opposite is true, if the reactants are too large, then mathematically we would get a Q that is smaller than K. And so we would see that we haven't formed enough products in order to be equal to K. We're always going to be comparing to K, comparing it to the equilibrium position. So if Q is less than K, that means that the reaction has to shift to the right. It's going to keep moving to make more products in order to reach equilibrium. And so let's try this out. So here's a sample problem for you. For the reaction of nitrogen plus oxygen in equilibrium with nitric oxide, NO, we're given a set of conditions, a set of molarities for each one of the substances, and the value of K. And the question is this reaction at equilibrium when if K is equal to 0.0025? If it is not at equilibrium, which way will it go in order to reach equilibrium? And so let's try it. I've written it out for us here. You can pause the video here and try it yourself. Plug in your values, solve for Q, compare it to K, and make a prediction. So, so I've written the conditions down. Q is exactly the same expression as K. Products raised to their coefficient, so concentration of NO2 squared, over the reactants raised to their coefficients. Nitrogen concentration and oxygen's concentration in the denominator. So my concentration of NO2, 0.03. Oops, that's not NO2. You guys letting me write down the wrong problem. Like, where does NO2 come from? Anyway, NO, 0.03 squared on top, 0.81 and 0.75 on the bottom. Grab your calculator, put that in. You get Q equals 0.0015. Okay, so answer the first question. Is this set of conditions at equilibrium? Well, we've got a Q of 0.0015. We've got a K of 0.0025. So no, that is not at equilibrium. Not at equilibrium. And so the second part of the question asks us, if it is not at equilibrium, which way will it go in order to reach equilibrium? Well, how do they compare? Our Q is less than K. So mathematically, that tells us that that we need to make more products. We need, in order for these two to be equal, then this reaction has to go further to the right, and so it has to make more products. So more products will be made. So basically what that's telling us is that we're at the point on the graph before equilibrium is reached. We are not there yet, and so more products are going to have to be formed in order to get to the point where we reach equilibrium. We would say, on your test, you would say something along the lines of, the reaction will shift to the right. To achieve equilibrium. Or you can talk about the amount of products that are made. When? All right. I'll be there in a few. Okay, so, yep, here it is on the slide. All right, so if we know K, then we can calculate the equilibrium amounts of our reactants and products. We can solve equations like we did yesterday. If you missed that fun little Zoom work time together, then you can take a look at that video. And so, how do I get this? Let's get this out of the way. So you can see the whole thing here. Tell you what, I'm not super great at this technology. All right, anyway, I think you can get the idea. When Q is less than K, the reaction is going to have to shift to the right to form more products. And when Q is greater than K, the reaction is going to have to shift to the left in order to form more reactants or to use up some of the products. And the goal there, of course, is to achieve equilibrium. When Q is equal to K, then it's K. It's at equilibrium. All right. So that's the deal with Q. It's not complicated. If you don't know that you're at equilibrium, then you can calculate it. You can predict which way the reaction will shift. So second big topic of the day, LeChatelier's principle. And this describes how a reaction shifts in response to stressors that are placed on the reaction. So if I change the pressure, or if I change the molarity, or if I remove or add reactants or products, what's going to happen to my equilibrium position? Which way will that reaction shift? And so lots of things, we can make lots of predictions using what we know about LeChatelier's principle. So here's the big idea for you. If it is disturbed, if a system at equilibrium is disturbed by changing the temperature, the pressure, or the concentration, then the system will shift to counteract the effect of the disturbance. So looking back at the reaction that we were just working with, so one particular stress I could apply to this system would be to add more nitrogen. Well, if I increase my concentration of nitrogen, I've added something over here, and the system is going to have to reply by shifting in the opposite direction. It's going to have to shift to the right to balance out that stress. If I take away a product, if I take away some NO, then it's also going to shift to the right to relieve that stress. If I've reduced my product, then I've disturbed my equilibrium, and it's going to reestablish equilibrium by shifting to the right and making more NO to replace what was lost. And so pressure and volume have the opposite effect, right? They're inversely proportional. As we increase the pressure, the volume gets smaller, and so we can think about both of those as being stressors on a system. Let's look. We need this slide first. Okay, so using this example reaction, nitrogen plus 3 hydrogen to form, this is our Born-Haber process to form ammonia. These are all in gas phase. And so look at the amount we have on both sides. I've got 1 nitrogen and 3 hydrogens. So I've got 4 moles of gas on the right side of my equation in equilibrium with 2 moles of gas on the product side. I think I said right, but I mean on the reactant side, 4 moles of gas. On the product side, 2 moles of gas. What's going to happen if I increase the pressure? Well, it's always going to, if I increase the pressure, then I am forcing those molecules to have more interaction with each other. I'm going to be putting them into a smaller container, right? So increasing the pressure would have the same effect as decreasing the volume. And that's always going to favor the side that has fewer moles of gas. So at either one of those conditions, if I reduce the volume or if I increase the pressure, it's going to favor the side with fewer moles of gas to reach equilibrium. So a nice little visual of that with our same N2O4 and NO2 equilibrium. This reaction has 1 mole of gas on the left, 2 moles of gas on the right. And look inside this chamber. As this piston is compressed here, the volume inside this container is getting smaller and smaller and smaller. Here we're at the maximum dark. Remember, the dark color is from NO2, but compressed even smaller, then it has to shift back towards the colorless reactants, and you can see that visually. That increasing the pressure past the point of equilibrium, we start to we'll shift it toward the side with fewer moles of gas. Okay, so Dingle has a nice chart for you in your packet. It's on page, let's find it, in packet 7. It is right here. It is on page 13 of 21 in the middle of packet 7. And so using